Hello and welcome once again for another ES340 video. This is day 22, part B. So we've discussed refrigeration cycles. Now we can also get into heat pumps. So the Carnot heat pump cycle starts out by noting, we can start out by noting that by the conservation of energy, we're going to have whatever the net out heat is going to be equal to the net heat in plus the net work done. In this case, again, assuming that we're ignoring we're ignoring KE and PE effects and things such as this, and the maximum efficiency for this type of not efficiency, excuse me. The maximum coefficient of performance for a heat pump, this is something that we've seen before, but we'll just reiterate, is gamma max is equal to the temperature of the hot reservoir divided by the temperature of the hot reservoir minus the temperature of the cold reservoir. Now, we can't, so this is for the Carnot heat pump cycle. As noted before, generally the Carnot type systems are not easily built. They're not easy to build for a variety of reasons. That's the case here too for the heat pump. So then we go to something like vapor compression, just like we did with the refrigerator. So we can do a vapor compression version of a heat pump, and it's the same kind of basic idea, right? We have an evaporator just like before. We have a condenser. We have a compressor, right? And we have some kind of expansion that's being allowed, going from step 3 to step 4. So, excuse me. So, very similar to the refrigeration cycle that we had before. And what we can do is we can find gamma from this, very similar to, let's actually write out what these components are. That might make things a little bit easier. In this case, it's Q out that we're going to be interested in over M dot, unlike the refrigeration cycle. So that's going to be the main difference here. Divided by the work done by the compressor in this case, because there's no, we're assuming there's no work at other stages. So this is what our coefficient of performance will be for the vapor compression type heat pump. A couple of key details here is that one, the coefficient of performance for the heat pump can never be less than 1, so keep that in mind. It could go off in theory to infinity, but as we know, in reality, nothing ever achieves a coefficient of performance of infinity because of the second law of thermodynamics, which you should at this point remember quite well, relating to the entropy, right? Now, the interesting thing here, though, that sort of makes the heat pump different is what is being used in the evaporator. Okay, and in this case, that can be a number of things that are easily accessible from the environment. An example of that is air. You might use the outside air in the heat pump. You might use lake or river water, or even well water, or even groundwater, right? If you can tap into the groundwater as the quote unquote refrigerant in this case, rather than using a refrigerant in order to make the heat pump operate. And heat pumps, by the way, can be quite efficient, both in terms of obviously the fact that you can just use local environment to help you, but also in terms of overall efficiency compared to, say, like an AC unit. A heat pump can, in theory, be quite efficient. The problem, the main problem that you have is, remember that the maximum efficiency is going to be related to the temperature of the hot reservoir. And depending on what ends up being the hot reservoir, say, like if you're doing a cooling application, it might be the environment. That means that your efficiency obviously is going to vary based on the outdoor temperature. So that's something to keep in mind. And similarly, if you're using it for heating, if you're going the other direction. So you can use a heat pump in both directions, much like for both heating and cooling purposes. Much like you can take any Carnot power cycle and reverse it to make a refrigeration cycle, right? So it's a similar kind of concept. Now this is an interesting one, and because we were talking about refrigeration, we'll talk about the Brayton refrigeration cycle. But the Brayton cycle actually, there are some key details that might be slightly different, but if you reverse the Brayton refrigeration cycle, you can get something akin to the Brayton power cycle, which is itself quite interesting. Not something that we're going to really cover so much here, but just know that this is one example. The Brayton power cycle, so going in the reverse direction, actually is something that can be found for jet engines, as an example. So when dealing with jet engines, a simple type of cycle that can be analyzed is the Brayton cycle. Okay, but we can also use this obviously for refrigeration cycles, and in this case, it's a gas type, as you probably picked up from the fact that the power cycle, the Brayton power cycle, could be used as a simple example of a jet engine. So because of that, obviously you need jet fuel to operate it. It's the same idea for the refrigeration cycle that you're going to use. So the power here in this case is going to be provided by gas. So and the refrigeration, the refrigerant itself, in this case in the refrigeration cycle, is also going to be a gas. So this should indicate to you that, we could use, and in theory, we could use any kind of gas as the refrigerant, including air. Air could be something that could be used in the Brayton refrigeration cycle as your refrigerant, as your working fluid in this case. Now this one actually shows, this diagram shows the ideal Brayton cycle. And you can see that you have a couple of constant pressure regions, right? So isobaric going from 2, I guess that the dashed line shows the non-ideal case, and the solid line shows the ideal case here, right? But in any case, notice that what you end up having is you have, as you go across the heat exchanger, you're doing this at constant pressure, so you must have you must have a constant pressure process here. Then you do then you have going up here, you have, oops, let me just pull that back down for a moment. Then up at the top here, you notice that you can go to the 2S state, which is the isentropic type state, going across the compressor. This is, again, something that we've been dealing with here. In the ideal case, the compressor and for the Brayton cycle, the turbine, are both isentropic, right? So, and you can see that in the diagram. In the real world case, obviously, that's not true. That's what the dashed lines show, is that you're not going to get exactly the isentropic process. You're going to get something slightly different, which is where the inefficiencies come in. Now, in this case, what you can do is you can go through the equations, but I'll do that for you. Basically, you have the notice that you're going to have work coming into the compressor in the Brayton refrigeration cycle. So that's what is powering the system. And what you have going out, the other side, is the power from the turbine. So you obviously have to spin that turbine. So you're losing some of that power, if you will, by spinning that turbine. And so your network going around the cycle is just the whatever went into the compressor minus whatever came out of the turbine. And that's what we have here. This should be WC. It's not quite clear, but that's what I meant there. So your network down here is given by the work done by the compressor minus the work done by the turbine. And obviously, as usual, your Qin dot is up here. And then you can see that if you look at these four pieces, well, again, ignoring kinetic energy, potential energy, all of that good stuff, then you come up with this following equation. Now, I do suggest that you go back and remind yourself of the equations, because we've done this before, but it's been maybe a little bit of time. So go back and see why it is true, going directly from the energy balance equation and entropy balance and all of that good stuff, why this would be true in this case, why Q dot is equal to this over M, and W dot over M is equal to what's in the denominator there. Okay. Now, the last application that I'll discuss that might be interesting for our discussion, now that we're analyzing real-world type systems, is the automotive air conditioning, and in this case using CO2 as CO2 as the refrigerant in this case. Now, your car AC probably does not have this particular type of setup, but in theory it could. And that's sort of a thing that's ongoing for automakers to make decisions on. What is actually typically used in your car is the same as is used in refrigerators commonly these days, which is refrigerant 134A. But we could potentially use CO2, and CO2 is obviously abundant in the atmosphere. While you're sitting breathing in the car, you're producing CO2. So this could in potentially in the future be something that's used as a refrigerant. So the abundance is useful, but actually coming up with a working process is a little bit more complicated. And you can kind of see that here, right? I have, it's not a simple four-stage cycle. Actually, I have six points that of interest, right? I go, again, I have a compressor here going from 1 to 2. I have some kind of cooler here where the heat is released. I have a heat exchanger. Notice that there's no mixing here. I do the expansion step, which is common, obviously. The evaporator again, but then I go back up through the heat exchanger. Okay, so this actually has an additional component in it, which is different from the vapor compression systems that we've been dealing with, in the fact that we have a heat exchanger in between, and it's not exactly the same as the cascade, right? Because the cascade was two connected to each other, and this is not exactly two connected to each other through two refrigeration cycles, vapor compression refrigeration cycles connected together. It's almost that, but not quite, right? It's the heat exchanger actually is an essential component of the whole system, rather than being something that brings two vapor compression systems together. But in any case, this uses gas, and as you can see, it has some potential. So that's all that I have for this video. Hope to see you again soon.